Hello, everybody. Today's lecture is going to be on chemical reactions, topic 4.9 for the AP curriculum, Oxidation, Reduction, Redox Reactions Part 1. Be sure to make sure you double check the standards and the objectives for this lesson, as I will be posting those on my website. All right, so we're going to be talking about two parts today. The activity series and specifically certain reactions about oxidation reduction. So we might actually have to break this video up in half, so just keeping everything kind of in check. So the first question is, what is the activity series? How do we know when a reaction will move forward? And the answer is most reactions are going to move forward if there is going to be some form of activity. And this activity is determined by how easily elements get oxidized. So oxidation, by definition, is the loss of electrons in elements, while reduction is a gain. And so whenever you want to figure out whether something is going to create a reaction, what you want to do is figure out how those electrons are moving forward. And elements can be listed in a specific way based off how reactive they are. And that determines how increasing or decreasing the activity is going to be a function. So here's a classic example of the activity series. If I go ahead and ask you why is it that copper versus iron, why is iron more reactive than perhaps copper? That has to do with its ability to move electrons around. As you go down this column here, you can see that potassium, who is a highly reactive element, has an easier way of oxidizing its element, which means that it's a very reactive element. And the one that you would probably not expect to have a lot of reaction would be gold and platinum, as an example. And you already know this because if you wear jewelry or you wear some sort of precious metal in your body, it doesn't actually turn green or it doesn't rust, doesn't have a lot of these other characteristics. For example, if you were to change it to iron or zinc. So activity series basically refers to how easily things get oxidized. Now, I highly recommend you somehow memorize these so that you can get a sense for what the reactivity is for each of these elements. How do we write activity series in a reaction? So if I ask you to predict reactions, the way you're going to do that is you're always going to have a situation where you're going to want to be able to react these elements and predict if there is going to be a reaction. And so let's take a look at the first example. Zinc, which is a solid, reacting with copper 2 ions in its aqueous form. And as you can see from here, whenever you write copper, you usually write it as an ion form because it's inside the solution. And if I ask you, am I going to get a reaction? The answer is you will get a reaction. And the reason why is because copper is going to interact with the zinc. And it will form copper solid as it becomes reactive, and the zinc ends up becoming a 2+. So here we end up having a switch. The zinc turns into the ion form and then the copper kind of comes out. However, if I switch this around and I give you the copper solid and give you the zinc, even though the zinc is more reactive, because it's already in its aqueous form, you're not going to have zinc come out. So you will not see zinc come out as a solid. And so general rule of thumb is that whenever you're taking a look at aqueous solutions, if that one is more reactive, in this case, such as copper, it's going to come out of that turning into a solid. Now, zinc is more easily oxidized than iron. So here's a classic example of something that you can find in real life. So if I want to stop zinc from rusting, from iron from rusting, what I would do is coat the iron nail or anything with a little bit of zinc to prevent it from rusting. And so that's how usually people prevent things like cars that rust. It's because you wanted to have that ability for the conversion of that oxidation. So you want to cover that metal that could easily be oxidized. So let's go ahead and talk about how you do these activity series in a chemical equation. So if I take a look at this example, copper 2 nitrate solutions poured over solid zinc, and I ask you, is this reaction going to be, first of all, you're going to have a reaction. And the second question is you're going to have is, what's the reaction going to look like. And so the first thing you want to do is, in this case, we're getting copper to nitrate, and we are going to be pouring it over zinc. So I want you guys to think about what I mentioned in the other one, that zinc obviously is a more reactive one. Are we going to get a reaction? And because zinc is in its solid form, it's going to want to turn into its aqueous form. And so the first thing we want to do is write down the half reaction for this. So the half reaction is going to be copper to ions. And so the way we do this is because we've already established that copper to nitrate will form into its ion form. You're going to have NO3, you're going to have copper in there, but usually you're just going to write down what happens with that half reaction. And so we pour it over zinc in this case to indicate the charge for that. And so if you take a look at this reaction, you can kind of see that zinc would actually turn into zinc 2+. And in order to balance this reaction, what you would need to do is make sure that the two electrons are going to cancel on both sides. So in this specific case, zinc is going to turn into its aqueous form because it's more of the reactive element versus copper. And because of that, you're going to end up with this total reaction. Now, how do we know it's a 2 electron? It's because you take a look at the transition metal, the Roman numeral, and it will tell you there that that's going to be what's happening with that electron. And so when you're trying to find these, you always want to figure out whether it's going to be on the reactant side or it's going to be on that one. But we already know that zinc is going to be the one that's going to oxidize, so it has to give out the electron. And so in this case, you have zinc 2+ plus Zn and Z+. You can automatically see that the copper now has changed. All right, another example is called halogen displacement redox reactions. And these are what happens when halogens are bonded to themselves, and they because they do that, they take electrons. In other words, they from oxidize any of the halides. And so if we take a look at this example, fluorine here, because this is at the top of the group in group 17, it's going to be taking electrons from any of the halides. And so you're going to see that a little bit carefully. So here's an example of chlorine gas bubbled through potassium bromide. So bromide is going to be our halogen here. And we automatically see that chlorine is going to take that electron in. It's going to form 2Cl minus. And we already know this because obviously there's those two chlorines. We're going to have that situation where we have to balance the equation out. And here you're going to see that potassium bromide, or KBr, it's going to break down into its aqueous form, Br minus, but because we need to have those two electrons, we're going to end up getting 2 moles of this. And so that's going to be our liquid form. And our answer here is pretty straightforward. I mean, you pretty much cancel out the 2 electrons, and you find out that your chlorine gas is going to be reacting with your bromide ions, and you're going to end up with 2 chlorines and bromide liquid. So that's going to be your half reaction that you're going to get. All right, our next one's called a hydrogen displacement redox. And again, this is all from the same family again. So if you take a look at those reactions, you're going to have the hydrogen atoms in H2O. And as they get reduced, they're going to gain electrons to form hydrogen gas. So water is kind of an interesting case, is where hydrogen is going to be displaced. And you're going to end up forming this. So for example, in this specific case, you're always going to be producing these hydrogen gas. And that's usually the reason why when we talk about ways of producing hydrogen gas, usually you're going to find things with like your alkali metals and then your calcium, strontium that's going to displace hydrogen. So really what we're doing is we're booting out this H out here to form hydrogen gas. All right, so here's an example of a hydrogen displacement redox. So sodium metal, if you place in water, is a highly exothermic reaction. Generates massive amounts of heat. And so if I ask you right now is write down the equation or the balanced half reactions for sodium, we're going to go ahead and do those real quick. So here we have water. Water is going to be adding to 2 electrons, and we already know that, based off the other equation, that we want to produce that hydrogen gas in there. Since we have water in there, we're going to be able to create your hydroxides and your H gas. Sodium, however, once you place it in water, you're going to form aqueous ions plus 2 electrons, as we already know that sodium has a +1 charge, so it's going to oxidize really easily. When it does that, it gives away 2 electrons. And your balanced reaction for this one is you're going to get 2Na, 2H2O, 2Na plus, 2OH minus, and an H plus. So carrying over the liquid form and the solid. And so the important thing here is just remember our net ionics, right? The key place here is that when you're dealing with this, you always want to figure out what you're producing, and this usually often catches on fire. That's why we kind of usually get that kind of highly exothermic. Well, the exothermic reaction is because exothermic, but if it does catch on fire, you kind of get that hydrogen gas bubbling as well. All right, our last one is going to be disproportionation reactions, or called I. And this is when an element in one oxidation state can go through both oxidation and reduction. In order for this to happen, at least there has to be an intermediate step that goes in. And so let's talk a little bit about an example of copper 1 chloride. And this is going to sit in a beaker for a very long time. So if you use some copper 1 chloride, dump it into the beaker, what happens with that copper 1 chloride? So overall, what happens is that if you put that in a beaker, it's going to break up into its ions for copper 1 and an electron, and you get that copper solid. Then what happens is that the copper is going to eventually break up again. So what you're going to do is get another copper here, and that turns into its aqueous form, and it's going to break into 2 plus and plus electrons. And so what you're really seeing here is obviously an oxidation reaction here. And if you actually do the entire reaction, what you're going to see is copper is going to automatically start turning into copper, copper plus, copper solid, and copper 2 plus. And so because copper has that ability to go back and forth between this, it's both oxidized and it's reduced. So going from copper plus to copper, copper is going to have a 0 charge. So in this case, it's actually getting reduced. But in this case, it's getting oxidized. So on this aqueous form, you're going to have both the copper solid and you're going to have the ion. So disproportionation reactions part 2, this usually involves 2 oxidation states and usually have an intermediate. And so the element must therefore have at least 3 oxidation states, and there must fall in between those. So here's another example of iron fillings. If I throw in some iron fillings and we're adding it to 0.5 molar of iron 3 chloride, how does that actually work? So here we go with the iron. So iron filling is going to be in an aqueous solution for the chloride. So again, chloride is going to be in aqueous ion form. We have the E minus. As we're doing this, since it's a 3, it's going to gain that electron in there. And then what happens there is you end up having an Fe2 plus. Now you take that Fe2 plus, and then what happens is then eventually we also have iron solid fillings, right? So that's coming from this side. That becomes iron 2 and 2 electrons. Once we do that, we're going to have to balance this reactions down, and you're going to end up getting this 2 Fe3 with the 2 electrons in the 3, and then you end up getting that situation. So here we have a lot of iron here that's being both oxidized. Our last one's going to be combustion reactions of organic compounds. And so here what you're seeing is methane is being burned in the air. And if I ask you how does that look in a combustion reaction, you can see that methane is a -4, +1, and so on. And you get to see that you're going to have this idea of the oxidation. So again, redox reactions can actually happen in many cases when you're producing something like an oxide. So sulfur here is going to be burned in air. You're going to produce SO2s. Calcium burned in air, you produce the calcium oxides. And so usually you're going to form these when you have in there. All right, we'll stop it right there, and then we'll continue part 2 in just a bit.